Okay, so we're going to be taking a quick look at how ions are formed and how we know what kind of charge they have, and how when we put those in compounds we need to be able to balance those charges out. So just a quick start to look at how atoms formed. We know that our protons have got a +1 charge, and our electrons they've got a -1 charge. So if we had something like hydrogen with its 1 proton, and then you've got electrons in the first shell, we know that we just need 1 electron there, which we indicate with a cross, because our 1 negative electron balances out our 1 positive proton. If we then move up to helium with its 2 protons, then we need the second electron there to balance that out, and we've now got 2 negative electrons and 2 positive protons. And of course what we're not interested in terms of charge is the neutrons in there, which balance out. Okay, so atoms must have the same number of protons and protons and electrons to balance out the charge. Now once we get to ion formation, we need to understand why atoms will lose or gain those electrons, and fundamentally it comes down to trying to get this kind of electronic structure. So helium is a member of the noble gases. So if we just bring up the periodic table here, so this is our periodic table, and we can see our noble gases down here on the right hand side of the periodic table, group 0. All of these have a closed shell or a full outer shell. So the very first period is the first shell. It can only contain 2 electrons, so helium has those 2 electrons, and that one's full. Our second period has 2 shells to fill up, and so this second one can contain 8 electrons, so our neon with its 10 electrons in total has electronic structure 2 and 8, so that fills that one up. And then the same for argon, the next shell can contain 8 electrons, and so that fills it up. So all of these elements down here on the right hand side, they have got a full outer shell, and this is electronically and energetically stable. All the other elements in the periodic table, they don't have full outer shells because they have partially filled shells. So when they react, either covalently, ionically or metallically, they want to try and gain an electron structure which is the same as one of these noble gases. So they can do that either ionically, by losing or gaining electrons. They can do it covalently, by sharing electrons. So there we go. So ionic is transfer of electrons. Covalently, that's our sharing of electrons. And metallic is when we have delocalization of electrons, and in all cases this leads to a full outer shell of electrons. So we've got a little program here which will help us understand this a little bit better. So if we take lithium in group 1 here, we've got our 3 protons because it's the third element. So those 3 protons give us a 3+ charge in the nucleus, 4 neutrons, which as we say are not relevant, they don't have any charge, and because we have 3 protons here we have to have 3 electrons to balance it out. So 3+, 3- overall, add those together and you get a 0 overall charge. And if we move through the elements, beryllium, that takes us to 4 protons and therefore 4 electrons, and again 0 overall charge. Oxygen will give us 8 protons and 8 electrons, fluorine the same, up to 9, and then as we just step through all of these we can see that every time there's more protons there's more electrons to balance out that charge. Now if we go back to lithium, in this case here we have a full inner shell. The first shell has got 2 electrons in, so that's the maximum it can contain, and then the second shell out, this is our outer shell, it's the one on the outside of the atom, it's only got 1 electron in it. So the easiest way for lithium to gain a full outer shell is to actually lose this one here. If we remove that electron, we can see that shell there has disappeared, so it was there to to accommodate that third electron. If we remove it, that shell disappears because it's no longer needed. So this becomes the outer shell now. So we have 2 electrons there, and that's the maximum it can contain. So this now becomes our electronic structure for a lithium ion. And we can tell it's an ion because it's an atom. It's got protons, neutrons, electrons, but now it's got a positive charge. So to improve the look of this, to make it look exactly how we want to be drawing it, what we need to do is how we would expect to draw it in the exam. We would write lithium, because now we don't need to write the contents of the nucleus. That's not important for the exams. We have our first shell, and now we have 1 electron there and 1 electron there. So this is our electronic structure of our lithium ion. So you can see here we've just got our 2 electrons there. And to indicate that it is in fact an ion, we need to show the charge. So it's got a 2+ charge, so we put a plus there, and then we put nice big square brackets all the way around that, just to indicate that the whole thing has got a positive charge. Now previously our lithium, down here, if we were to draw the lithium atom, cross and cross, and then this is the lithium atom. The electronic structure of this we can also write as 2, 1. Now up here we've only got the 2 electrons, so we just write it as 2, but again we need to show that it's got a positive charge, so we put the square brackets around it and draw a plus. And now we can see that we have achieved this electronic structure, the same as the noble gas. So if we've got 2 electrons, the noble gas with that structure is 2. Now note here that even though this has the same electronic structure as helium, so if we were to draw helium over here, helium has got its 2 electrons, and that has an electronic structure of 2. This lithium here is not helium. It's still lithium because it's got the 3 protons in the nucleus. It's just lost an electron, and therefore it has the same electronic structure as helium, but it is not helium, it's still lithium, and so this is now our lithium ion. Okay, so we can go through exactly the same process with all of those elements. So let's take oxygen for example. Oxygen, we have the 8 protons and 6 electrons in the outer shell, and now for this the easiest way for it to ionically fill that outer shell is to add on 2 electrons. Now we've got 10 electrons, making it -10 overall, plus 8 from the protons, so the overall charge is now -2. So if we were to draw that in a similar way to here, we would start with our oxygen and our first shell of electrons, and then our second shell of electrons. Let's do it in green this time. So we've got 1, 2, 3, 4, following the north-south, east-west convection. So that will be our oxygen atom with its electronic structure of 2, 6. And now to turn it into a ion, to fill up the outer shell, we need 2 more electrons here. So we add 2 electrons, which will have come from a metal somewhere, and it's still oxygen in the middle. And now our outer shell has got 1, 2, exactly the same as before. And it's now picked up the 2 electrons from somewhere else, and so we indicate them as a different picture. Our electronic structure now is 2, 8, and because this whole thing here has got a 2 negative charge, we show here on the electron structure it's got a 2 negative charge as well. Okay, so exactly the same process for any of these: lithium, beryllium, sodium, magnesium, aluminium. All of these as metals will lose electrons, so 3 for aluminium, that will lose 3 electrons. Chlorine, 7 electrons in the outer shell, it will add 1 electron onto that, and that will form the full outer shell. Sulfur, 6 electrons, just the same as oxygen, add 2 electrons in, and there you have your full outer shell, sulfide ion. So the formula of all of the ions, you should hopefully have noticed that the group 1 elements here, they all have 1 electron in their outer shell. Group 2 elements have 2 electrons in their outer shell. Group 3, 3 electrons in their outer shell. And so these will lose 1 electrons. Group 1s therefore form 1 plus ions. The group 2, because they lose 2 electrons, they are the 2 plus ions. And the group 3, they form 3 plus ions. Whereas over here in group 6, they are missing 2 electrons to get to that full outer shell. So 6 add 2 will get to your full outer shell, whereas 7 just needs 1 electron, so that will get to the full outer shell. So anything in group 6 which forms an ion will form a 2 minus, anything in group 7 will form a 1 minus ion, and obviously our noble gases won't react ionically. So that explains why the ions form and how they form. So the last part of it will be forming balanced formulae for our ionic compounds. So if we take the example of sodium, which has a 1 plus charge, and chlorine, which has a 1 minus charge, if you put those two together as NaCl, then this already forms a nice balanced compound, because we've got a 1 plus charge here, we've got a 1 minus charge here, and these two cancel each other out, so we don't need to change the number of these here. If we go to sodium and oxygen as an ion, so this is still 1 plus and this would be 2 minus. Now if we put a sodium and an oxygen together, just the two of them, we've got a plus and we've got a 2 minus, so put those two together we end up with a 1 minus. So overall this formula would be NaO minus. And this is unacceptable. We have to have a neutral compound, we have to have the charges balanced. So the best way to think about it is if you've got a 2 minus charge here and each sodium only provides a 1 plus, then we need to just add in an extra sodium here. So balancing this out, and then we've got 2 pluses and 2 minuses, so overall this would be Na2O. So now we have plus, plus and 2 minuses, and overall that balances out as 0. So a couple more examples of that one. If we took calcium and chlorine, calcium's 2 plus, chlorine's 1 minus. So this time we've got 2 pluses here and only 1 minus here, so again let's add an extra chlorine in to balance that out, and we end up with the formula CaCl2. Slightly more complicated one, if we take aluminium with its 3 plus charge and oxygen with its 2 minus charge, these two don't balance out very easily. If we put a second oxygen in there, we get a 4 minus here and a 3 plus there, so that doesn't help. So we need some more positive charge in. Let's put that in. Now we've got 6 plus here and 4 minus here, so that still doesn't work. But one more oxygen balances that all out nicely, and so we can end up with Al2O3. So that all balances nicely. But this trial and error sometimes is a bit convoluted. So there's something that we call the crossover rule, which allows us to do this much more quickly. And the crossover rule works best when we have these numbers up here. And so if we have a look at this number 3 up here, we can see that that 3 has transferred or crossed over from where it was as the charge up here to the number of oxygens required down there. And if we take the number of negative charges on the oxygen, it's crossed over the line to the 2 there. So if we write that formally out here, Al3 plus and O2 minus, and then if we cross over the oxygen and we say, sorry, the 3 plus, and say that needs to be down here, and the 2, that needs to cross over, there's the crossing over, that needs to be down there, we end up with our expected formula Al2O3. Okay, so this works with all of them. It will even work up here. So if we have our Ca2 plus and our Cl1 minus, let's write in the 1 now just to make it very obvious. Our 2 goes down to how many chlorines we need down here, and our 1 crosses over down to the calcium, and so we end up with the formula Ca1 Cl2, and when we have a 1 in the formula we don't write it for convenience.